Hello friends, so this is your second lecture on convective heat transfer, and as we discussed in the last class, today we will be looking at the derivation of the governing equations. So we will start with the conservation laws in thermodynamics that we derived for an open system and try to mathematically formalize the derivation using what is called the Reynolds transport theorem, which is a general expression for conservation equations in control volumes. Okay. And what we will try to then do is to use mass, momentum and energy equations for specific control volumes using the Reynolds transport theorem, but do that for an infinitesimal control volume from which we can derive the differential equations for motion and energy conservation. In doing that, we will also look at the kind of similarities that exist between conservations of mass, momentum and energy. So this is one module that would cover some basics of fluid mechanics which are underlying the study of convective heat transfer. Okay. So that is the plan for today's talk or today's lecture. Let's see how much we are able to cover in today's class, and maybe if things spill over, then we'll do it in one more lecture. Okay. So now let's move on to the presentation, move on to the whiteboard. So we had derived conservation equations for open systems, which looked something like d by dt of MOS is equal to, we had written it in the form of del by del t. I'll write it in partial differential form. I'll explain it to you why it comes in that form when we go to the mathematical detail of it, of m. Okay, so this started with MCS, okay, and from that we derived the MOS. So this is MOS plus summation over all inlets of m dot I minus summation over all inlets. Okay, this is m dot E and minus summation over all inlets of m dot I, because we had said that this is equal to this minus this on the right hand side. So now when you bring it all to the one side, this becomes this is equal to 0. So this is your equation for conservation of mass that we had derived in the conservation equations for open systems. In the same way, we had done d by dt of EOCS, okay, which is according to the first law equal to Q dot in plus W dot on, and this we derived it as equal to del by del T of EOS plus summation over all outlets of m dot E minus summation over all inlets of m dot I. So this is we had derived. Similarly, we had done d by dt for the second law of SCS is equal to, which should normally be equal to summation over boundary segments of Q dot J by Tj, okay, and plus sigma Cs, and this we equated it to del by del T of SOS plus, okay, so here EI and EE and EI, something which was plus summation over all outlets of m dot ESE minus summation over all inlets of m dot I SI. So this is something that we had derived. Okay, so this is something you may remember, and you may also remember how we derived it. We derived by considering an open system and a closed system which contains all the mass that would enter the system between time t and delta t together as the closed system at time t. So at time t plus delta t, that mass had entered and some mass had left. So we had considered those to do that. So if I try to generalize that, so suppose I have a boundary that is drawn here, and this is, let us say, the closed system at time t. Also, it's the open system at time t as well as t plus delta t. So it's the same boundary which constitutes the closed system at time t, open system at time t. So they are coincident. But at time t plus delta t, the closed system would have moved, but the open system remains the same window. So suppose at time t plus delta t, let me say at time t plus delta t, let me say the closed system has moved this much. Okay. So then if I call this as region 1 and this is region 2, then region 1 contains all of that mass that has entered the open system at time t plus delta t. Okay. And the region 2 contains all of that mass that has left the open system at t plus delta t. Okay. So if I say that the velocity field in this situation can be drawn something like this. Suppose there is a flow that's happening, and in the flow I am looking at a region which is given by this closed system at time t, or open system at time t and t plus delta t. So this is the window that I am looking at over a period of time. So if I try to write the conservation equation for the open system, then that would contain the conservation equation for the closed system plus what has entered, that is mass 1, and plus what has left, that is mass 2, and each of them can actually be looked at on the basis of the velocities in those directions. So suppose I take that this is a small area, okay, which was outside the open system at time t, but between time t and t plus delta t, as the closed system moved, so the magenta control volume that I have drawn, which is the closed system at time t plus delta t. Okay, let me just do that. Okay, so this is Cs at time t plus delta t. Okay. Now, nothing enters or leaves the closed system. That is the definition of the closed system. So the same mass that was contained in the black enclosure at time t is contained in the magenta enclosure at time t plus delta t. So if I am looking at the black line as the open system, at time t it was coincident with the closed system. At time t plus delta t, because of this mass moving and there is a certain velocity, some amount of fluid has entered the open system. It would still remain outside the closed system, of course, because closed system does not allow mass to go in and out. So this is the amount. So suppose this velocity is a velocity vector v. Okay, so let me not write using different colors. Let me just write using black. Okay, so suppose v vector is the velocity vector which is a function of x, y, z and t, okay, is the flow field that I have around. Because of that, the mass that is entering would have a component which is normal to this boundary at any given location. Okay, so suppose this is my boundary and this is my velocity, okay, and the normal to the surface, let us say, can be drawn like this. Then the normal component is the component that would have an angle theta. So I can say V, if I take the magnitude of V and take its cos theta, okay, then that would be the component which is normal to the given area. So if I have an elemental area dA that is here, then dA cos theta into V would be the mass flow that is entering through that, and since that is entering over a time period of delta t, the m dot E, because now the n is in the outward direction, so if the component is in the same direction as n, then it is mass that is leaving. So if I can say d of m dot E, okay, this is going to be equal to the amount of mass that crosses this boundary, or rather this boundary, over this time period t plus time period delta t. Okay. So what would that be? That would be equal to the mass that is contained in this elemental region. What would that be? That would be dA, okay, multiplied by what moves in at V cos theta. Okay. So the volume of this will be, the length of this will be equal to, the length of this would be actually equal to V cos theta times delta t, and the cross sectional area is dA. So the volume is V cos theta delta t into dA. Okay. So that is the amount of fluid that would have entered during that period of time. Okay. And this is dme, it's not dm dot E, this is dme, the amount of mass that is entered. So this is the volume, that multiplied by the density of the substance is this. So if I take the delta t to this side to get the rate expression, so I'll write this as this divided by delta t, okay, and take limits as delta t tends to 0. This is delta me by delta t. And take limits as delta t tends to 0, you would get an me dot, which is equal to rho V cos theta dA. Okay. So this is the amount of mass that would have left through this. So depending on the direction of the velocity, whether the direction of the velocity is inwards or outwards, say for example, if I take this part of the boundary, the velocity is outwards, and if I take this part of the boundary, then the velocity is inwards. So automatically there will be a sign that will take care of what mass enters and what mass leaves. Similarly, on this side there is a mass leaving, and on this side there is a mass entry. So the integral over the entire boundary of this quantity, which is basically integral of rho V cos theta dA over the entire area, would actually be the net mass leaving the control volume. Okay. So if I use that, then I'll be able to write the expression which initially we had written in the form of summation of m dot E minus summation of m dot I, which is what we accounted for as the net mass leaving the system. Okay. This would basically be written now by integral over the area of the control surface. Okay. So if I write this integral over the control surface area of rho V cos theta dA. Okay. Now if I want to write it in the vector form, this V dot n dA would actually be V into dA into cos theta. Okay. So I can actually replace this V dA cos theta with this V dot n dA. So this becomes integral over the control surface of rho v vector dot n vector into dA, where the n vector is the unit normal vector to the area at any given location, dA. So, when this is integrated, you get this. So, your equation then becomes d by dt of MCS is del by del t of MOS plus this integral. Okay, and this quantity itself, if I can take the density to be varying continuously inside the control volume, then this del by del t of MOS can be written as del by del t of integral of rho dV over the control volume. Okay, so then you get this expression, which is the rate of change of mass in the closed system is equal to the rate of change of mass in the open system plus the boundary flow term. Okay, so that will give me the final expression as dMCS by dt is equal to del MOS by del t plus integral okay, let me write it in the way that we had written. This is del by del t of integral, you can actually put a triple integral over the control volume of rho dV plus integral double integral over the control surface, because this is an area integral, of rho v dot n dA. Okay, so this is a more formal equation for this one. So basically this is what we call as the Reynolds transport theorem corresponding to conservation of mass. In the same way, if I write for the other expressions, I am not going into details to derive that. I can write dECS by dt can be written as del by del t of triple integral over the control volume of rho E dV. Okay, so E is the energy per unit mass plus the integral over the control surface of rho E multiplied by V dot n dA. Okay, so if you compare these two, you find that this quantity per unit mass is the thing that we are looking at in this one. So if I am writing at this mass, this is nothing but 1 into mass per unit mass. Okay, so so the mass per unit mass in this particular case is unity. So there is a 1 term here, so I can put a 1 in this one, and similarly there is a 1 that is here. In this case, that is going to be E, because this is going to be MCS into ECS. Okay, so this is ME. So this is E per U is my energy per unit mass. This is, if I write M into MCS into 1 mass per unit mass, so then it becomes the equation. So basically this is the same equation with only the quantity which is per unit mass that the conservation is written for is changing from one to the other. So if I write the second law in the same fashion, you get D into MCS into SCS, okay, by dt, which is dSCS by dt, is del by del t of triple integral over the control volume of rho S dV plus double integral over the control surface of rho S into V dot n dA. Okay, so that is your expression. So in general, any quantity B, which is m times beta, where beta is the B per unit mass, then we can write this expression as dB by dt is equal to del by del t of triple integral over the control volume of rho beta dV plus double integral over the control surface of rho beta v dot n dA. Okay. Now this is the general theorem called the Reynolds transport theorem. Okay. When beta is equal to 1, it becomes a conservation of mass equation. When beta equal to E, it becomes the conservation of energy equation. Beta equal to S, it becomes the second law. And this can be extended also to the other quantities. And the general equation for this would then be this dB by dt is given by the basic physical law that governs it. And that would be equal to this quantity, which is when it is considered for a control volume in a flow field. Okay. So this is the Reynolds transport theorem. So when I go back to the energy equation, this dEcs by dt, which is this, is also going to be equal to q dot in plus w dot on. Okay. So that is your first law. So now the first law for an open system in a flow field would contain these. Then you expand this q dot in and w dot on corresponding to the control volume that you are looking at, and accordingly you get the energy equation for that control volume. Similarly, the second law as this quantity, and this should be equal to integral over the control surface of dq dot by tb, where tb dqb dot by tb, where the q dot b is the energy going in through every elemental control volume dq dot dq, every elemental control volume dA. So this is integral or integrated over the entire control surface, where tb is varying with the control surface, plus sigma dot cs. So this is your expression that you will write. So when I write this whole thing together, I'll be writing the second law for an open system in a flow field. Okay. So in the same way, we can also extend this to conservation of momentum or angular momentum. In conservation of momentum, of course, the B is the momentum, which is mass multiplied by the velocity vector, which has three components, of course. So it will be mass multiplied by IU plus JV plus KW. So if I take I, J and K are the three unit vectors in the x, y and z directions respectively, and U, V and W are the x, y and z components of V, then you can write this. So this is actually a combination of three terms, m dot U, m dot V and m dot W. Sorry, mu, mv and mw, okay, which is basically the momentum in x direction, y direction and z direction respectively. So if I write the vector equation for this quantity as in the same form as the Reynolds transport theorem that we have written here, and beta would then be u for the x direction, v for the y direction and w for the z direction, and overall it will become the magnitude of the velocity. Then you should be able to write the momentum equation in vector components in x, y and z directions, because this b written in this form will actually give rise to three sets of terms, one with I vector, one with j vector, one with k vector, which is corresponding in three different directions. So you get three components of the momentum equation: x momentum, y momentum and z momentum. And what is the conservation of momentum equation according to Newton's second law of motion? dB by dt for a closed system is actually equal to the summation of forces that are acting on the particular control volume. So this is going to be equal to del by del t of triple integral over the control volume of rho magnitude of v. So it will actually be rho v dv. Okay. So this vector, this velocity is a vector, so it has three components, u, v and w, and plus integral over the control surface of rho v vector multiplied by v dot n dA. So you get the V vector twice, once here and once here. This becomes a scalar because it's the scalar dot product of this one. This has three components, I, j and k. So if I split this in x, y and z directions, I'll get one with u here, one with v here and one with w here. Similarly, one with u here, one with v here and w here. This v dot n will change according to the x, y or z directions. So accordingly the component will vary. So you'll have the components of x momentum, y momentum, z momentum according to the control volume. But this will give rise to three equations, and this would be the conservation of momentum equation that we will typically write. In the same way, if I write angular momentum also has three components, okay, the x component, y component and z component. And therefore, if I write B as the angular momentum, then angular momentum per unit mass would be the torque in that direction, and this is the summation of torques, and this again is a vector quantity, and the summation of torques would be written in terms of the momentums in each direction. So you can actually write any conservation equation using the Reynolds transport theorem and write conservation equations for the flow systems. So this was necessary because whatever we had done in thermodynamics was more informal for a small control volume, where we considered inflow and outflow just as discrete quantities and then summed up over them. Whereas in flow field, it's a continuous quantity, and therefore you need to formally integrate it and obtain this. Now, the Reynolds transport theorem that we wrote in this can be derived very easily using the simple properties of partial derivatives, okay, in mathematics. So let us try to do that and get the correspondence, so that those of you who have a flavor for mathematics should be able to appreciate this as well, and those of you who have a flavor for physics can appreciate whatever I have already done. So then the two are equivalent, and knowing the two are equivalent will also give you an idea of what the mathematics and physics shake their hands like. Okay, so now let's come to the let us say any quantity b, which is a function of x, y, z and t. You can have two kinds of derivatives for this one. Let's try to appreciate this. Suppose there is a quantity which is a function of x, y, z and t, and I'm trying to measure it. So suppose, let us say you have a stream of water flowing through a pipe, and you need to measure the temperature of water. Okay. Now this gives you a philosophical question, which is the water, okay, because there is a pipe, let us say, and there is water that is flowing, and I would like to measure the temperature. What we normally do is to put a thermometer into it and measure the temperature here. Now whose temperature am I measuring? Because when I started measuring, I had some packet of water, let us say, which was here, and before the thermometer could stabilize and read some temperature, it takes some time, and over this period of time, this packet probably has gone here, and some other packet which was somewhere here has taken its place. Now the temperature that I am reading, the temperature T, it could be a function of x, y, z and t, because the temperature that I read in each of these I should be able to plot as a function of time as something, and I should be able to measure the temperature at different locations, and each of them would be a function of temperature like this. So temperature is a function of x, y, z and t. So this is a quantity which is a field function, and when I'm trying to measure it, if I measure it here, then I'm measuring the temperature of one location through which several particles keep passing through, right? So I am not measuring the temperature of one lump of water, but I am measuring the temperature of one window in that flow field, whose temperature keeps varying with time, and the x, y, z are given by that. So this is one way of looking at it. You are measuring the temperature at one location irrespective of which particle of water that is going through. Another approach would be to sit on this particle, okay, with a thermometer on it and go along with it wherever it goes. Okay, so you keep measuring this. By the time it reaches here, I would have gotten its temperature, and it would be the temperature of that water, but its XYZ coordinates keep changing. Okay, so when it was at that X, Y, and Z, and at that time, it had that temperature. Okay, so this is the other way of looking at it. So the first one that I looked at it is a field description. Okay, where I take a small window in the field where there is movement of substance, and I'm describing the properties of that location in the space and time rather than following a particle. In the second case, I follow a particle, so it is a particle description. So in mathematics, you call this as the Eulerian description and this as the Lagrangian description. Okay. In the case of thermodynamics, we called this as the closed system description and this as the open system description. So the translation from the closed system to the open system is what we are trying to look at now. So if I have a property B that is changing with time, so I call dB by dt, that is, let us say the temperature of this particle. Okay, when I started it was here, and then by the time I finished measuring it came here. I have measured its temperature. Okay, so now how its temperature varies with time is something that I would like to measure. Then, since this B is a function of x, y, z, and t, I should be able to write it in terms of the derivatives of this B partially with respect to each of those variables and write the relationship. So in mathematics, we normally write this as dB by dt. Okay, in order to distinguish it from the field derivative, the substantial derivative is often written using the capital D in fluid mechanics, just to distinguish it from the local derivative. So this is dB by dt, which is going to be equal to del B by del T dt. Okay, sorry, del B by del T, okay, plus del B by del X into dx by dt plus del B by del Y into dy by dt plus del B by del Z into dz by dt. So this is something which we commonly write in mathematics. We recognize that this dx by dt, dy by dt, and dz by dt are given by the three components of the velocity. So this will be u, and this will be v, and this will be w, where velocity vector v is iu plus jv plus kw. Okay, which is nothing but dx by dt, where x is the location of this particle. Okay, this x is nothing but x, y, z, and t. This is a function of this. This is the location of or position of the particle, dx by t, and this is going to be equal to I del x by del t plus dx by dt, sorry, I dx by dt plus j dy by dt plus k dz by dt, because this x is given as xi plus yj plus zk, where x, y, z as are all functions of time. So then the rate of change of its position is given by this. So this is your velocity vector. This is your velocity vector, and that velocity vector is going to be equal to this iu plus jv plus kw, that is that. So if I look at this, this is u, v, and w. So if I look at this quantity, this I can write it as V dot del operated on B, where this del is I del by del x plus j del by del y plus k del by del z. Okay, so that is this operator. So V dot this would actually be u times del by del x, v times del by del y plus k w times del by del z of B. That is what we get here. So you get this as equal to del B by del T plus V dot del into B, V dot del operated on B. So that is your expression that you get from basic mathematical derivation of this. Now, if I apply this expression to control volume and integrate it, okay, then I can write this B as beta into dm, where dm is rho dV. Okay, so if I write B is equal to or dB is equal to beta times dm, which is nothing but rho into beta times dV. Okay, so then the quantity B will be an integral of this. So B will be an integral over the control volume of rho beta dV, which I can substitute for B in both of these expressions. So then I'll get dB by dt. We wrote it using the capital D. dB by dt is equal to del by del T of triple integral over the control volume of rho beta dV, which is something which we have already written. In addition to that, we have V dot del of, again, triple integral over the control volume of rho beta dV. Okay. Now, using the Gauss divergence theorem, this can be written in terms of the surface integral. So, if I have V dot del, the derivative of this volume based quantity, according to the Gauss divergence theorem, this becomes equal to integral over the control surface of rho, which remains there, rho beta, into V dot n into dA. Okay, so that is basically what you'll get. So if I use the Gauss divergence theorem on this term, a volume integral getting converted into surface integral, then you get this plus this as this, and which is the same as the expression that we had derived in the previous slide, which is this one. Okay, so you get the same expression as this and this. So that is your Reynolds transport theorem. So from basic mathematics, by just applying the property of partial differential equation by partial derivatives, and by using the Gauss divergence theorem, okay, where the divergence V dot del of a volume integral can be written in terms of rho, the surface integral of V dot, the normal to the surface dA. So this when applied becomes the Reynolds transport theorem that we had derived. So you can see that this substantial derivative, which is basically the Lagrangian derivative, is equal to the Eulerian derivative, which is the field description of that quantity, plus the term that is corresponding to the fluxes of that quantity through the control surface, right, which is written as this. So if I come back to transport in flowing system, this is the rate of change in an open system. So if I have a control volume or an open system in a flow field, so there is a velocity field and I have a control volume, the rate of change of beta inside this is given by this term, and this term basically gives the net outflow of beta through the boundaries of this control volume, which is basically outflow minus inflow. So the two added together is the substantial derivative dB, and this should be equated to the external forces or external things. So depending on the law that you are using, if it is conservation of mass, then the rate of change of mass, unless mass is produced or destroyed, is equal to 0. So conservation of mass will basically mean this is equal to 0 when beta is equal to 1. And if I write conservation of momentum, then this whole thing would be equal to the summation of all forces. So if I'm writing it as a vector term, so in x direction it will be equal to the summation of x forces, y direction it will be equal to summation of y forces, and so on, with the beta being equal to the respective velocity component. That is the momentum equation. And for the energy equation, this will be the energy per unit mass, and the right hand side will be q dot and w dot terms for the control volume that I have considered, and so on. So that is the mathematical background or basis of the Reynolds transport theorem, which can be used for the derivation and simplification of governing equations for conservation of various quantities in a control volume in the flow system. Okay. So I hope that brings the formalism to a certain level of clarity. Now, using this Reynolds transport theorem over an infinitesimal Cartesian control volume, I'll show you how the conduction equation can be derived when the flow is absent. Okay, and then when the flow is present, let us look at the conservation of mass, momentum, energy equations. I will not derive all of those equations because that's a time consuming process in itself, and may not serve too much purpose for this course. But what we will do is to write the final equations that are normally used in fluid mechanics. Okay, so now let me apply this conservation equation to an infinitesimal control volume over which we let us say derive the heat conduction equation. So this is an infinitesimal control volume inside a bulk of a certain solid which is having no motions. So the velocity vector is equal to 0. Okay, so there is no component of velocity. So if I look at the Reynolds transport theorem, then this term will completely disappear. Okay, so it will basically be just this term and equal to the heat and work terms that are there. Since it's a solid, there is no work also. The del by del T of this will be actually equal to the heat flux, the heat term. So basically, if I write the Reynolds transport theorem for this, it will basically be del by del T of rho E dV integrated over the control volume is equal to, because the second term, because the velocity vectors are 0 in conduction, so we are now deriving the conduction equation. For the case of conduction, the velocity vector is identically 0 because there is no movement of the medium. So this would be equal to q dot in plus w dot on. Okay, and for this control volume, we had said, okay, the q dot in has 6 components: 1, 2, 3, 4, 5, and 6. And we found the net outflow from each of these. So net inflow from each of these will be written in terms of this is, let us say, q dot x and q dot x plus delta x double prime, that is per unit area, and with the area multiplication I'll have this will be delta y delta z, okay, and so on. So this q dot in and w dot on is a 0 quantity. So if I write only for one of the directions, it's actually q dot x double prime minus q dot x plus delta x double prime multiplied by delta y delta z. Okay. Likewise, you have two other terms in the y direction and z direction. Let us say q dot double prime y and q dot double prime y plus delta y multiplied by delta x delta z, and similarly q dot double prime z and q dot double prime z plus delta z multiplied by delta x delta y. So let us take one of these terms, okay, and this would actually be written in the form of delta y. This q dot x can be written as minus k del t by del x at x, and this will be minus of minus plus k del t by del x at x plus delta x. Okay, and this, if I do the integration, assuming that this rho e remains constant because it's a very small control volume inside that, I take it out, I'll get a delta v, which is delta x delta y delta z. So I'll get a del by del t of rho, this e is, let us say, CVT at this moment. Let us just take E as U because there are no potential kinetic energies, into delta x delta y delta z, and that will be equal to this multiplied by delta y delta z. So okay, if I divide throughout by delta x delta y delta z, this will go off and this will become 1 by delta x. And if I take limits as delta x tends to 0, I'll get a del by del x of k del t by del x on the right hand side, and that is my one-dimensional conduction equation. And if I put all the three terms, I get the three-dimensional conduction equation. Okay, so this is the way the conservation of equation can be directly used to draw the derive the terms that are present in the conservation equation for a control volume in a flow system. And when the v is non-zero, then there will be an additional term that corresponds to the rho e multiplied by v dot z, v dot n dA, and the v dot n dA would correspond to, for this control volume, for example, u, because the dA would be delta y delta z, and v dot n would be u because v is ux plus vy plus ui plus vk vj plus wk, and this q dot x is in the I direction, so v dot I would actually give me u, right? So it will be u multiplied by the area, which is delta y delta z. So you will have a rho u delta y delta z multiplied by the energy that is coming in from that side. So you would have, in addition to the conduction terms, you will have a convection term or the advection term that brings in the term. So that is the point of doing the Reynolds transport theorem. In the conduction equation, that term is absent because v is 0, so that is not there. But in the full energy equation, you will have the terms that is corresponding to the flow term. So let us just try to write one dimension of that. So you will have del by del t of rho e multiplied by delta x delta y delta z plus the integral over the control surface. Let me perform by assuming that over the left control volume where qx is there, let us say the flux is uniform over the entire, so or the flow is uniform over the entire thing. So I can write this as rho u, okay, which has come out on this side, multiplied by delta y delta z. Okay, so this multiplied by e, that is there. So this would be there at x minus this is what is coming in, and this would have a negative sign because it's the normal vector is in this direction and the heat flow is in this direction, so it will have a normal negative sign, plus I'll have rho e multiplied by u delta y delta z at x plus delta x. Okay, this would be equal to, let us say, delta y delta z multiplied by minus k del t by del x at x plus k del t by del x at x plus delta x, okay, on the right hand side. So now if I divide throughout by delta x delta y delta z, this delta x delta y delta z will also go, this delta y delta z will also go, but there will be a 1 by delta x here. So that will be rho e u at x plus delta x minus rho e u at x divided by delta x as delta x tends to 0. So I will get a del by del t of rho e plus del by del x of rho e u is equal to del by del x of k del t by del x. This is for the x direction that I would have got. So this is for convection in one dimension, in x direction alone. If I have the y and z directions also, then I will get two more terms like this, del by del y of rho e v and del by del z of rho e w will get added here. There will be two more terms. Similarly here we will get two more terms added, del by del y of k del t by del y and del by del z of k del t by del z. So that will become the full three-dimensional energy equation in the absence of any work term. Okay, if the work has to be considered, then that would convert this E into H. That is something that we have already seen in the one-dimensional conduction equation. In addition to that, the control volume that we have looked at, because of the fluid flow, can have shear forces of various kinds because of the fluid motion, and also you can have the normal forces because of pressure and the stresses that are there on each surface. So the body forces and the surface forces that are present on the fluid control volume can do work on that, and you need to have the energy equation including the work done by the body forces and the surface forces included there. So that will make the energy equation complete. So I hope you get an idea. So let's not go further and derive the entire set of equations, but I will write down these equations for a reasonably simplified form of thermodynamic energy equations. So let me write it for 3D incompressible steady flows. Okay, so this is an approximation that I am making. The word incompressible has a very special connotation. We will just describe that before we write the equation. So we are all aware of compressibility or incompressibility of fluids. Okay, so suppose I take air. Air is a compressible fluid. Why is it? Because if I take a certain volume of air and I apply force on it, then the volume of air would change, okay, and the change would be substantial. Okay, but suppose I take a liquid or a solid and apply forces. For a mild amount of forces or moderate amount of forces, the change in volume can be neglected. Okay, so then under certain circumstances, when the forces are not enormously strong, these substances, the liquids and gases, can be considered as incompressible fluids, whereas the gas can never be considered an incompressible fluid because the change in volume is substantial even with small or moderate amount of force that is applied on it. So you get what is called an incompressible, is a compressible fluid. Okay, so this is about fluids being compressible or incompressible. So that is a property of the substance. So we look at what is called the bulk modulus, okay, which decides whether the substance can be called compressible or incompressible. If the bulk modulus is basically it's a ratio of stress by strain. Okay, so just like you write for linear extension, you write the Young's modulus, the stress by strain. For bulk modulus, it's actually for the volumetric change, and therefore if the bulk modulus is small to moderate, we call it a compressible fluid, and if the bulk modulus is very high, then you call it as incompressible fluid. Okay, so that is quantity that we normally look at. So if a fluid is compressible or incompressible, that can be determined by one property called bulk modulus. But we are talking about flows being compressible and incompressible. So what do we mean by a compressible flow or an incompressible flow? When there is a movement of substance, let us say water flowing through a pipe, then there needs to be some pressure difference delta P, which is there between the two ends of the pipe, in order to drive this flow. Okay. Now this delta P, we'll have to see whether it's large enough to produce any change in the volume, or in that sense the density of the substance. Okay. So for example, if I take water flowing through a pipe, even with let us say a 50-meter long pipe or a 100-meter long pipe or even a kilometer long pipe, the total pressure drop along that pipe would typically be in the order of a few hundreds to a few thousands of pascals. Okay. But the atmospheric pressure itself is about 10 to the power of 5 pascals, and we know from our properties of water experience that until about 50 megapascals of pressure, the density of water hardly changes with pressure. Okay. So in that sense, the pressure differences that exist here are good to drive the flow, but are not good enough to change the density of the substance. Okay. So such substances, similarly for airflow, you can have small changes in density, small changes in pressure in the airflow because of pressure drops. Okay, suppose I have an airflow through a pipe, there will be a pressure difference between the two ends of a pipe, which would be of the order of a couple of pascals, a few tens of pascals, but that is not good enough to cause any substantial change in density. So only when the change in density that is caused by the change in pressure is about, let us say, 10% of the original density, then we consider the flow to be compressible, otherwise incompressible. So that happens when, for gases, the velocities are comparable to the speed of sound. Okay. So the sound waves propagate by waves or compression and expansion of the gas molecules or gas volumes. So acoustic velocity is the speed at which small disturbances propagate through the medium. Okay, so suppose I have a speaker here and it produces a small pressure pulse. This pressure pulse travels at a certain speed, which is called acoustic velocity through the medium. For sound waves or just small disturbances at room temperature and pressure, the speed of sound in air is about 330 meters per second. Okay, so if the pressure difference caused by velocities has to reach about 10% of the change in of the current density. So if the air density has to change by 10% because of the pressure disturbance, then the velocity of the fluid that is there needs to go to about 1/3 of the acoustic velocity. Okay. So under normal room conditions, pressure and temperature, this would be of the order of about 110 meters per second. Okay. So unless the velocities are that high, even air flows can be regarded as incompressible. Okay. So the equations that I write now would be normally valid for most engineering situations pertaining to mechanical engineering, but not quite pertaining to aerospace engineering, for example, where the speeds of flow and speeds of movement are substantially higher. Okay. So that is the meaning of incompressible. So an incompressible flow is one in which the pressure differences caused by the flow do not change the density substantially. Okay. So for that matter, even compressible fluids like air can undergo incompressible flows so long as the velocities are not extremely high. Okay. So let me just quickly write down the equations of conservation of mass and momentum for 3D incompressible flows, and we'll stop there. We'll continue using those expressions in the next class. So your steady state equation for incompressible flows for conservation of mass looks like del U by del X plus del V by del Y plus del w by del z is equal to 0, where you remember u, v and w are the three components of the velocity vector, x, y and z components of velocity vector. Then conservation of x momentum. The momentum equation would have three constituents. I would only write the conservation of x momentum right now, which will basically be del by del x, or let's say u del u by del x plus v del u by del y is equal to minus del p by del x plus mu by rho, 1 by rho del p by del x minus 1 by rho del p by del x, okay, plus mu by rho times del squared u by del x squared plus del squared u by del y squared plus del squared u by del z squared. Okay, I missed one term here, which is w plus w del u by del z. So the equations of y and z momentum equations will look very similar, except that this u would get replaced by v in the y momentum equation and w in the z momentum equation. The others would remain the same, and this x would become y or z in the y or z momentum equations. These u's will become v or w in the y and z momentum equations. So those are the equations. Okay, so in the assumptions that I wrote in the previous page, with constant properties. So these are the assumptions that I have now taken: three-dimensional, incompressible, steady flows with constant properties is the assumption that I have taken. So with that, I get conservation of mass as this, conservation of momentum looking very similar to this, and conservation of energy. I'll write it to the next page. Okay, again this will look like u del t by del x plus v del t by del y plus w del t by del z is equal to k by rho Cp multiplied by del squared t by del x squared plus del squared t by del y squared plus del squared t by del z squared plus q dot triple prime by rho Cp. Okay, so this is your this one. What we have done here is to neglect work done by pressure and viscosity. Okay, so we actually said that the external forces, body forces and surface forces do work. So in incompressible flows, normally the work done by pressure is negligible because the volume is not changing, and we have also neglected the work done by viscosity, which will be important where there is a heat generation because of dissipation of work due to viscosity, which is more important in applications like bearings and places where there are high shears. But otherwise, these two terms are usually negligible in most situations, and therefore we have dropped those terms. So this is your energy equation in three-dimensional steady state with constant properties. So this is your conservation equations. Okay, so we'll stop at this point in today's class. We have actually done derivation of what is called the Reynolds transport theorem, and using that Reynolds transport theorem on small control volumes, tried to derive the energy equation as a demonstration. The conduction equation we derived, and we also showed what will happen when the convection terms are included, and then I wrote the governing equations with some assumptions for conservation of mass, momentum and energy. Okay. Okay. So these are the equations that one needs to solve in order to get the temperature field and the del T by del Y that we talked about, the gradient of temperature normal to a surface, which is required to find the heat transfer coefficient analytically. Okay. So these equations would be tools. We will not go into complete solution of complex differential equations, but we'll try to understand what the solutions will behave like by doing some orders of magnitude analysis and try to understand the way the solutions would look like for different circumstances starting from the next class onwards. So we have now got some arsenal in our stockpile that we can use for attacking the problems that are related to convection heat transfer. Okay. So we'll stop here and continue in the next class.